Hello, this is Cretis Jenkins, and I want to welcome you to our presentation featuring highlights from a 2019 ERTech paper with a provocative title that prompts us to ask, do we really squander billions on unconventionals? Well, unfortunately, the answer is yes. You don't have to look any farther for confirmation of this than the Wall Street Journal. A 2019 article noted that 29 oil and gas companies that they tracked spent $112 billion more in cash than they generated from operations over the past decade. This was attributed, in large part, to optimistic forecasts that failed to capture the profound variability in well performance. And, to be more specific, these companies failed to understand whether the average well was going to be a commercial success before they committed big dollars to development. So how do we avoid making this type of mistake in the future? Well, it starts by applying a staged approach as shown here. This approach exposes capital in an incremental fashion, increasing significantly with each stage. We use 4 stages, shown in the black font, and an associated threshold with each stage shown in green. At each decision node, shown by the black squares, a decision must be made whether to continue. The yellow circles show that there's a chance of success and failure associated with each of these. Discipline is critical in applying this approach. If a project is going to fail, you want it to happen in the early stages before you commit to development. Conceptually, it's pretty simple, but companies find it very difficult to consistently implement this process. And why is that? Because companies feel significant pressure to minimize the time and money spent in pre-development. This can lead to decisions based on intuition, recent experience, or rules of thumb, which are susceptible to being affected by cognitive biases. In our haste to put iron in the ground, we're often overconfident and overoptimistic about what can be achieved. And because most of us are doing this, we consistently overpromise and underdeliver as an industry. So how do we effectively implement this staged approach and deliver on our promises? It begins with exploration, which involves identifying basins with working petroleum systems and their associated unconventional fairways. We build and overlay both volumetric and producibility plane maps, and then use composite maps like you see here to estimate play chance and prospective resources. Based on this work, multiple vertical wells are typically drilled to discover movable hydrocarbons and delineate the extent of the accumulation. A detailed example of this process is discussed in a newly released ERTech paper focused on the Barmer Basin in India and referenced in the upper left-hand corner of this slide. The next stage is appraisal, the purpose of which is to drill a series of horizontal wells and demonstrate that the average rate from these wells exceeds some predetermined threshold, such as recovering the well cost. Consider a lease that is 50 miles long with 15 horizontal appraisal wells. We can display their initial rates on a log probability plot as shown in the lower left-hand corner of this slide. A straight line indicates a log normal distribution of rates, which is typically what we see. Note the slope of the line, which is relatively flat, indicating a large variance. In fact, we can quantify this variance using the ratio of the P10 value to the P90 value on the plot, which in this case is 14. This is a large value suggesting there are significant changes in rock and/or fluid properties across the lease. So we investigate these, and what we discover is that there is a reservoir pressure gradient across the lease that strongly affects well production. Using this, we divide the lease into 3 areas of 5 wells each, and then plot each set of wells separately. When we do this, we get 3 separate trends, shown in the graph at the bottom center of this slide, with each trend having a steeper slope and a lower corresponding P10-P90 ratio of about 5. What matters for our decision making is not the performance of these individual wells, but rather the mean value of each 5-well program as shown in the plot on the bottom right. It's clear from this plot that Area 3 should be our focus. But how confident can we be, with just 5 wells, that a subsequent development program will meet or exceed our required economic threshold rate of 300 barrels of oil per day? To answer this question, let's consider 4 examples of 5-well drilling programs shown here. In each case, we will sample a distribution with a P10-P90 ratio of 5 and a mean initial rate of 350 barrels of oil per day. To be clear, if you sample this distribution hundreds of times, the mean well will have an initial rate very close to 350 barrels of oil per day. This is the state of nature. But let's imagine we've not yet determined this. All we know, as we begin drilling, is that the average well from our drilling program must have an initial rate exceeding 300 barrels of oil per day in order to meet our appraisal stage threshold. What's the chance, then, that a 5-well program sampled from this distribution will achieve this rate? The most common result of sampling this log normal distribution is seen on the upper left, where numerous poor wells sample the low end and 1 or 2 wells sample the high end. What you hope is that you'll drill 4 or 5 wells that have high rates as shown in the upper right. But this rarely happens because you have to sample the high end multiple times in a row. You might also generate a distribution like the one on the lower left, showing an increasing initial rate with additional wells, or on the lower right showing a decreasing initial rate with more wells. Both of these are the result of randomly sampling this distribution. However, if you're not maintaining consistent drilling and completion practices, you might believe that your engineers have cracked the code on the lower left, or should be finding another line of work on the lower right. Neither of those conclusions are valid in these cases. Instead, you've simply been fooled by randomness into thinking a meaningful trend is present. Finally, note on this slide that the 5-well program in the upper left has an average initial rate of less than 300 barrels of oil per day. This is a false negative, since we know that drilling more wells here will eventually result in a mean initial rate of 350 barrels of oil per day. Since we want to avoid walking away from an opportunity like this, how many wells should we plan on drilling in the appraisal stage in order to have 80% confidence that the average well will exceed this threshold when we develop the lease? To answer this question, we can sample our original distribution more than 5 times and see how this affects our confidence. In the upper left is our original log normal distribution. If we sample this 5 times, calculate the mean of these 5 values, plot the result, and repeat this 10,000 times, we get the graph in the upper right. In effect, it shows us the outcomes of 10,000 5-well programs. Notice how the P10-P90 ratio has decreased. More values are within plus or minus 10% of the mean, and the distribution is becoming more symmetrical. If we sample our original distribution 25 times, calculate the average of these 25 values, plot the result, and repeat this 10,000 times, we get the graph in the lower left. And finally, if we sample our original distribution 100 times, calculate the average of these 100 values, plot the result, and repeat this 10,000 times, we get the graph in the lower right. In effect, we are simulating 10,100 well programs in this graph. As you can see, by drilling larger well programs, we reduce the uncertainty of the average outcome, which is converging on the mean. We can then take the P90 and P10 values shown on each of these graphs, divide them by the mean of 350 barrels of oil per day, and plot them versus the number of wells drilled. And when we do this, we generate what's called a trumpet plot. By connecting the values, expressed as percentages, we create upper P10 and lower P90 bounds that converge with more wells. The separation between these bounds is referred to as uncertainty around the mean. It represents our 80% confidence interval and is centered along the 100% confidence line. We can then take our resulting frequency plots and use them to estimate the chance that a well program will meet or exceed a given threshold, as shown here. For a 1-well program, given a P10-P90 ratio of 5 and a mean of 350 barrels of oil per day, there's only about a 48% chance that our initial rate will exceed 300 barrels per day, which means that 52% of the time, we will walk away from this commercially viable development if we only drill 1 well. If we drill 5 wells, there's a 64% chance that the average well will exceed 300 barrels per day. With 25 wells, this increases to 87%, and with 100 wells, it's 99%. We can then extract the values of 48, 64, and 87% from 3 of these frequency plots shown here, and use them to build a confidence curve on the next slide. The 3 black dots on this graph are plotted at the confidence values extracted from the previous slide. A line drawn to connect these dots shows that to attain 80% confidence of exceeding the threshold rate of 300 barrels of oil per day for a P10-P90 ratio of 5, 18 wells will need to be drilled. If the P10-P90 ratio is 4, 80% confidence can be attained with just 12 wells. If the P10-P90 ratio is 10, 80% confidence requires more than 30 wells. How do you know which P10-P90 ratio is most appropriate for your reservoir? Well, it depends on the data you've gathered, the modeling you've done, and those reservoirs you believe are most analogous to your own. It's fair to say that greater uncertainty should lead you to drill more appraisal wells in order to develop greater confidence that the average well will be a commercial success before you move on to the demonstration stage. Then, as we enter the demonstration stage, the goal becomes to optimize well spacing, which is the lateral separation between wells, and well stacking, which is the vertical separation between wells. We also want to validate our appraisal stage production type curves, improve well performance, and drive down well costs by 30 to 40% relative to the appraisal stage. It may also be useful to implement several variations in order to test different development concepts. A good example is the South Hudson project by Anadarko Petroleum in the Denver Basin, which is shown here. 3 different reservoirs are being targeted: the B and C chalks in the Niobrara Formation and the underlying Codell Sandstone. The illustration includes demonstration projects ranging from 14 to 30 wells per square mile and varying amounts of completion fluid ranging from 12 to 36 barrels per foot of lateral. These projects are critical for determining which well configuration is most profitable, and they contain enough wells to overcome some of the variability caused by local changes in reservoir quality. Assuming commercial success in the demonstration stage, these projects can then be expanded in the development stage. Once we commit to development, a key surveillance tool is the sequential aggregation plot, which is shown here. The purpose of this plot is to ensure that the results from new wells are meeting expectations. The plot boundaries are the aggregated P90 and P10 initial rates as a function of the number of wells we intend to drill. As we drill our wells, we accumulate the results to see if the drilling program is delivering a cumulative initial production rate within the range of expected outcomes. If not, we need to pause the program and understand why. Finally then, we highly recommend adopting assurance and look-back processes. These not only help facilitate the staged approach, but they also allow us to disseminate learnings within the organization and continually improve the quality of our decisions. In summary then, large amounts of capital have been squandered by companies making poor decisions about how many pre-development wells they need to drill, which leads to poor decisions about continuing or exiting a project. What we've presented here are a series of tools and steps that can help you improve this process. These include applying a staged approach, the principles of aggregation, trumpet plots, confidence curves, and sequential aggregation plots. To assist in applying these tools, we offer a number of services for clients including training, software, and consulting. In particular, our Unconventional Reservoir Assessment and Valuation course and ProjectRA software teach and apply the key principles outlined in this presentation. We invite you to check these out on our website and contact us if you have any questions. Thanks for watching, and please let us know if we can help you better manage risk and uncertainty in your next unconventional venture. Good luck!